postdoc at the University of Auckland, and my main research interest in the empirical labor economics and applied microeconomics, development economics, and some well-being of workers. And here I'm doing some policy evaluations. So this is my email address. Please feel free to send me your questions regarding the lectures today. Right. I'm going to start with a simple question: what is econometrics? Because strange as it might seem, there does not exist a generally accepted answer to that question. From the silly question like econometrics it is what econometricians do, to the answer like econometrics is the study of the application of statistics, mathematics to the analysis of economic phenomena. What this means? This means that econometrics and econometricians wear many different hats. First, they should be an economist, which are capable to utilize economic theory in order to improve the empirical analysis and to address the problem that they are looking for. Second, at any time, they should be mathematicians and to formulate economic theory in a way that make it appropriate for statistical testing. And at times, they should be applied statisticians spending hours with the computers and trying to estimate economic relationships that of interest. And finally, they should be as well theoretical statisticians that applying the skills that need to develop statistical appropriate techniques appropriate to the empirical problems. So based on the, I just need to do this as a based on the model, he provides this description, and this he says that this is an application of statistical and mathematical methods to the analysis of economic data. Or put it simply, for those who are starting for the first time with econometrics, this is just a combination of mathematics and statistics, and it's all about data, and it's all about measurement. The origin of econometrics and econometrics analysis can be traced back in time with the works of the 19th century political arithmeticians such as William Pitt and Gregory King, Sir Charles Davenant. The first attempt to quantify economic analysis is attributed to Gregory King, who basically looked at the relationship between deficiencies in the corn harvest and the associated changes in corn prices. And this is the first demand schedule, which is commonly known as the Gregory King's law, and is published by Davenant. What is interesting is that the data, the King's data, are remarkably not only because they are the first of their kinds, but also because they perfectly fit cubic regression of price change on the quantity changes. So the Econometric Society is formed later in 1933, and this is how they define the econometrics, which is economic theory and its relation to statistics and mathematics. So you can see from the next slides, this is just first introduction lecture today, but you're going to see that we need a lot of mathematics and statistics in order to estimate our models. How does one go about structuring an empirical economic analysis? It may seem obvious, but it worth emphasizing that the first step when we sit and start with an empirical economic analysis, it's a careful to formulate our question of interest. It should be economically based. It should be based on consume theory. Second, we need to hypothesize, and later we're going to discuss the way we hypothesize different questions of interest. There might be various hypotheses which can be formed in terms of the unknown parameter. On step 3, we need to formulate mathematical model. We need to use mathematics in different equations in order to describe the relationship of interest. So this here could be different depending of our research question. We can set up different mathematical equations. And most important is step 4, which is data collection, because under empirical analysis, use data to test the theory. And finally, we test our model having the data, and I'll give you more examples in the coming slides. We test this empirical questions of our interest by different models. And in this way, we basically test the theory. Schematically, this is presented by this graph, which slightly repeat what I just said. So important, we need to start with our question of interest. We need to base the research question on economic theory. Importantly, comes the mathematical model of that theory. We need precisely to describe what is our dependent, what is our explanatory variables. We need a careful mathematical model. Having the data, collecting data, we need to put this this mathematical model in a practice and test it. And next steps is final step to forecast, to predict, and to make general conclusions based on our model. If one example that starts with the very basic statement of economic theory is the Keynes, who postulates that there is a positive relationship between the income and consumption. So you can see that first we start with some theoretical question of interest. We're going to look at the relationship between the consumption and income. And what Keynes postulates is that if an individual's income increases by $1, the consumption will increase, but as well, but less within $1. So there's something called marginal propensity to consume, which lies between 0 and 1. So, and then second, once I carefully set up that I want to look at this relationship, and this is my question of interest, I need to express mathematically my relationship. So I start with a simple linear regression model where I can carefully need to define what is my dependent variable. In this case is the consumption expenditure, and I normally use Y to express this, and then I define what is my explanatory independent variable. In this case is income. When I define in this equation beta 1 and beta 2, this is called the parameters of the relationship of this equation, and in that particular case beta 2 measures the marginal propensity to consume. In the next lectures, which is starting with the simple linear regression model, we're going to discuss in more details all these parameters of interest. So I just want to give an example how we start with the empirical analysis. So in the second step, as I said, we need the data. To obtain these values of our beta 1 and beta 2, we need the data. So this is just a simple example data in here, which represents the personal consumption expenditure, which we defined in our case as Y, and the gross domestic product, which we can express in our case as X, which explain the consumption. So having in hand this data, we can easily go back and estimate the model here. So finally, once we estimate the model, we need carefully to interpret our results and to conclude based on the model. This is just a starting point on what we're gonna look at in this course, how we do estimate and how do we predict based on observed data. But let me, before move to this, let me first say more about what type of data basically we use in economics and in econometrics in particularly. We're going to start with the time series data. You might be familiar with this, but I just need to revise this as part of this introductory course. With the time series data, we have many. We have collection of data at a specific points in time. So once we observed a data on some variable ordered by time, we call this a time series. And for example, the example of this time series data like gross domestic product, consumer price index, stock price index, money supply, and so on. What is important is like this is data that are collected at the regular time intervals. They are either daily, weekly, monthly, quarterly, annually. And another important feature for those of you who in future continue working with the time series is that time series data makes them more difficult to analyze as compared to the cross-sectional data, which I'm gonna explain in the next slide, because the economic observations can the economic observations can really, if ever, be assumed to be independent across time, and most of these time series are related often strongly to their past histories. That's why we need to go to more additional manipulation as testing for stationary and non-stationary, but we're going to see this in later discussions. So once we have data observed by a time, we call this time series data. One example for time series data going to look like this. For example, the money supplies in the United States between 1951 and 1999 can be expressed in this trend behavior. Another example, again, with the time series data is this data plot, which describes the UK pounds US dollar exchange rate. This data contains about 598 observations, and we can easily pick the main feature of this data by looking at the chart. We can see that there is a stable, like, we can see that there is an attempt by the UK government to hold the exchange rate fixed until a particular year, until the end of 1971, and there's a gradual depreciation of this pound after that. And anyway, and this point of what is important is for you is just to look at this data and to make to be able to distinguish between time series data and the next set of data, which we call cross-sectional data. This cross-sectional data mainly used in the labor by labor economists, and these are data that are characterized by individual units. For individual 1, for YI, which is individual, could be from 1 to n, we collect different characteristics, we collect data. For example, for a sample of individuals or a household, could be firms, could be states, but the specific they are taken at a given point in time. For example, in 2010, I I make a labor force survey in Egypt, and this is going to be cross-sectional data. I collect specific questions. I ask specific questions about individuals, whether their gender, what is their gender, their concerns, their ethnic background, and so on. These are data that we call cross-sectional data. And then we come to another type of data, which are post-cross-sectional data, and those they have both cross-sectional and time series component. Example of this, for example, we collect household survey data, but again, one collected in 1985 and another collected later. So we pull this together, and normally by pulling this data together, we increase the sample size, we increase the exponential power of the sample, and pulling cross-section from different years is a very effective way when we want to analyze the effect of, for example, new government policy. Once we have data from the 2 years before and after, we can run a simple difference in difference and see whether the policy program is effective or not. So this is one of the advantages by pulling together to cross-sectional data. And finally, we have something called panel data or longitudinal data. This combines the both time series and cross-sectional component, but the distinguished feature here is that we basically have the same unit, the same individual as in the cross-section, but we observe this individual, we follow this individual over time. For example, again, I go back to my survey in Egypt, but basically, once I survey this in 2010, I repeat the same individuals. I go and survey the same individuals 2011 and so on. So I construct something like a panel element of my cross-sectional data. An example of this some wage, education, employment history. So by going back and repeating the survey in 2011, basically, I'm going to ask again whether you're employed and unemployed, and I'm going to construct a history, an event file of all these individuals. So this is something that we call panel data, and respectively, this sort of data requires something different estimation methodology. In this table, basically, I'm trying to distinguish what is the difference between the qualitative and quantitative data, because it's important to make this difference now. So the qualitative data, basically, they deals with this description. They can be observed, but this data can't be measured. For example, color, smells, taste, appearance, beauty, and so on. And normally we convert data, and we convert this data into the numeric data by constructing something called dummy variables, and they are measured by either 0 if we observe the event, if we know whether this is a gender male or female, and no and 0 in the other case. And the other type of data we call quantitative data, and these are the data that deals with the numbers. These are the data that can be measured. So it's important for you to make the distinguish between these two, the qualitative versus quantitative data. So the quantitative, for example, it could be the weight, the speed, time, the temperature, humidity, sound, and so on. It depends of your research question of interest. Once you handle the data, it's very important how it's very important how you're going to express, how you're going to present this data. So it is important for you to have some basic knowledge about the descriptive statistics or some scatter diagrams to plot and make it readable. And once we talk about the scatter diagram X or Y plots, this is a very first way to express something, to express whether there is a relationship between two or more variables, because economists are often interested in this, if there is some sort of relationship between this sort of variables. For example, we might look at whether the high education level is associated with higher earnings. Do countries with a high population density also tend to have high deforestation rate? And this is one example that I'm looking at here. I'm having data about the deforestation and population density for 70 tropical countries. So I want just to plot one of these variables versus another one in that plot, and we're going to do this later in this data. But what I want just to start with now is just to show that how by having this XY plot I can say whether there is some sort of relationship between these two variables. So each point of this graph represents deforestation and population density for the one country, and then I have 70 countries in that plot. So what I want to highlight here is that the graphical methods can be very useful to draw some simple aspects of the relationship between two variables here. And what we can see, there is a positive relationship between X and Y. So countries with a high population densities have higher deforestation. Since the high population density might increase the pressure to cut down the forest for some more wood, which basically is logical to expect this positive relationship right here. But graphical methods can be useful. However, in many cases, it is important to be numerically precise and express. And in econometrics and in statistics, we use some basic descriptive statistics, such as the mean. You might know what is the mean, but I just want to summarize right here that this is a statistical term to express the average, and this is the formula that we use for the mean. Most of the softwares nowadays, even Excel, can calculate this for you, but it's important for you to understand what's behind this calculation. So we denote the mean by Y bar, like this one, and this is the summation of all yi and y from 1 to n over the n, which is the sample size. So for example, the data, we have data for GDP per capita over 19 countries, and we want to see what's the average of this GDP per capita. We basically gonna take the summation of all the GDPs that we observe for each of these countries over the sample size, which in our case is 90, and we're gonna compute something like this value for the mean. The concept of mean is associated with the middle of the distribution, and we use as well quite often some other descriptive statistics as the median, which is basically the middle value, and basically this splits the distribution into two equal halves. And the mode, which is very another useful statistics. The mode is simply put the most common value among some variables, and if there is no most common value, the mode will be just the highest point in this histogram. In the next slide, I give a simple example. For example, if we have 7 people and they report their annual income like this, 18,000, 15,000, 9,000, 15, 16, 17, and 20,000. So the mean is going to be the summation of all these values over their number, which is this case is a 7, and the median, which split the distribution into 2 equal halves, is going to be the 16,000 pounds, and the mode, which is the most common value in this case, is the 15,000. This is just simple calculation on this descriptive. There is the mean or the average figures, however, hides some important deal of variability across the countries. For example, the example with the GDP and the deforestation, if I want to look at the average, this is going to hide some important features like the mean and the maximum, because some countries might have very very low GDP per capita as compared to others. So there's another useful statistics are the minimum and the maximum, and by looking at the distance between this minimum and maximum, we can derive to something called standard deviation. We can see how dispersed is the distribution. So the standard deviation, which is the variation on the dispersion of the set of the data values, is expressed by this formula. Again, although in practice you never have to calculate this, you might find it useful just for your knowledge. Again, we take the mean of y bar and the square of this difference over the n minus 1. And another useful descriptive here, which some statisticians confuse by saying the standard deviation and the variance. The variance is just the square of the standard deviation. What is important for you is just to know these measures of dispersion. They measure the spread, the variability, or the inequality. Basically, most of the econometric study, most of the papers, they report the mean and the standard deviation, and this gives an indication for the variability of your variable, which basically we can express this by having this normal distribution plot, and where the mean is the middle of this distribution. So you can see that one standard deviation, how the one standard or two standard deviations away from the mean going to look like. So from this away from the mean. Once we start this in the data, I'm going to show you how basically you derive this very easily from the software. There's more advanced descriptive statistics, which we can summarize as following. For example, for any chosen country, let's say in Egypt, you can ask yourself, okay, how many countries are poorer than Egypt, or what proportion of countries are poorer than Egypt? If you ask some question like this, then this question is equivalent to asking what percentile Egypt is at. So basically, you need some descriptives like percentile or quantiles. The quantiles points in a distribution relates to the rank order of the value of that distribution. And if you ask yourself about the question that I just stated, at what percentile Egypt is at, then you need this percentile descriptive, which is descriptions of the quantiles relative to the 100, and basically you divide the data range up into the hundreds, where the X percentile is the data value such that this X percentage of the observations have lower data than the other have lower data values. So accordingly, we have 15 percentile of the mean, which is the mean, which is the median value of the distribution. Here there is a mistake in the slides, which I'm gonna correct the 15 percentile again, but this is not the mean. The 0th, the 9th percentile is the minimum, and the 100th percentile is the maximum of the distribution. And consequently, there's another descriptive code, quartiles, which divide the data into quartiles. So we have the first quartile, which is the 25th percentile, and we call this the lower quartile. We have the second quartile, which is the 15th percentile, and we call this the median quartile. We have the third and the fourth quartile, and the fourth quartile basically is equivalent to the 100th percentile, or this is the maximum of the distribution. With this graph here, actually, I plot. This is one graph that is based on my estimation on return to education for females in Russia in 2003. But what I just want to show you here is how I do express this return to education by using the quantiles of the income distributions. If we think in a way that at the top of this earning distributions are more able individuals as compared to the bottom, where we focus on the lower or low educated individuals, the distribution gonna look something like this. So it will gonna be higher for those with the higher earnings or for the higher education level at the top. This quantiles measure in this way help me to present the earning distribution in that way. There's other descriptive statistics other than this, and we use something called interquartile range, which, as the name suggests, measure the difference between the third and the first quartile. Again, here is the example with the GDP data that I use, and I can upload on the Blackboard for you to have it. For example, by using this interquartile range, I can conclude that 75% of the countries have GDP per capita less than $9,800, which falls into the third quartiles, and about 25% have less than $1,162, which falls into the first basically quartile. We have as well another measure called deciles, and deciles divide the data into the tenths. So basically, we have the first decile. We have the first decile, which is equal to the 10th percentile, and for example, the 8th decile is going to be equal to the 80th percentile. The 9th decile is going to be equal to the 19th percentile, and so on. And finally, I already mentioned about the minimum and the maximum. By having the minimum and the maximum, we may take the difference between this and compute something called the range of this data. Another measure in econometrics that is widely used, you might find it useful in your analysis, is something we call correlation. This is an important way of numerically quantify the linear relationship between two variables. But what I want to highlight is basically that you need to distinguish between correlation and causation, which will come in the next slide. So we measure the correlation by having this formula. For some of you it might seem complicated, but what you need to know is that the correlation between this x and y is expressed by the ratio, and again in this formula the y bar means the y and x bar are the means of the x and the y. So you need to have your means calculated based on the formula that I provided earlier on over here. So the means, once you calculate the means, you can easily calculate by hand, or if you want to test your knowledge, the correlation between these two variables. What is important to remember is that this correlation always lies between -1 and +1. So the positive values of R are going to indicate a positive correlation between X and Y, and a negative values are going to indicate a negative correlation. When we have R equal to 0, then this means that the two variables are uncorrelated. The larger positive values of R is going to indicate, of course, a stronger positive correlation. And when we have R very close to 1 or equal to 1, then this indicates the perfect positive correlation. And I'm going to show you in the coming slides how this looks like in a graph. The more negative values of R indicate strong negative correlation. So R equals to -1, again, is going to indicate a perfect negative correlation. When we have correlation between Y and X, this is exactly the same as having the correlation between X and Y. And this is what is important to understand later once we start with the regression analysis, because when we run a regression, it's important to have this Y fixed, because there's Y and X. In this case, Y is stochastic. And here, these two variables, they are randomly chosen. So it doesn't matter whether we're going to take the order of these two variables, doesn't matter. And it's important the relationship between these two variables. And if we take the correlation between any variables, Y and itself, is going to be equal to 1, of course. So if we want to look this by having knowledge on the XY plots, and I'm going to show you how you do this in Stata later on in this course. So you're going to have a positive, we're going to have an upward sloping pattern. When you measure your relationship, then this is going to indicate you that you have a positive correlation. The downward sloping pattern, once you plot these two variables, is going to indicate a negative correlation. And by having a strongly correlated variables, you're going to see how they fit or they are close to the straight line. And of course, weakly correlated variables are going to be less, more scattered. What I'm talking about is this here. So, for example, this is an example how you're gonna look like by having a perfectly correlated variables. So all the points gonna lie exactly on the straight line. Please note that this slide does not correspond to actual economic data. They are artificially created just for you, because normally this is quite rarely happen in econometrics. But this is how your data is going to look like when you have perfectly correlated variables. This XY plot shows you two positively correlated variables. R equals to 0.51. Our correlation coefficient is 0.5, which is slightly moderate correlation. But this, you can see that there is a slightly upward sloping pattern here. However, the points are widely scattered, but overall we can conclude that there is a moderate positive correlation between these two variables over here. The next plot shows you two uncorrelated variables. The correlation between these is absolutely 0, so they are not correlated. They are randomly scattered over the entire plot. Finally, in this graph, we can see a negatively correlated variables. So this correlation between these two variables shows downward slope. and the correlation coefficient is minus 58. But what is important once we plot these variables for you is to be able to analyze and to indicate what's the sign of these two variables. Are they correlated? And if they are correlated, just to guess what the correlation is, whether it's a positive or a negative. These figures basically indicates one way of thinking about the correlation. Basically, it indicates how well a straight line can be fit through the XY plot. So you can see that variables that are strongly correlated fit close to the straight line. If I go back to this slide, which I called about the perfect correlation, but anyway, it's just you can see that these variables strongly correlate and they fit very close to the straight line, which is with upward trend over here. So the variables that are weakly correlated is going to be more scattered. It's going to be like this. So all this XY plot simply indicates you what is the correlation, what is the relationship between having two or more variables. To understand the correlation, I give for my students some more examples in the class. But here again, if we look again between this deforestation and how this relates to the population density, if I run this in other side, Excel or in this data software, it's gonna give me, or if I want to calculate the correlation ratio by hand, I'm gonna get a point like 0.66. which indicates a positive linear relationship between the population density and deforestation. So which again I can continue and continue and give more insight what this positive correlation is going to mean. This means that the country with a high population density will tend to have a higher deforestation rate, on opposite countries with low population density tend to have a low deforestation rate, and this is logically to expect. So you might sit and think and develop some examples of correlation coefficients between any two variables of your interest in order to test your understanding of this. We move to the magnitude of this R, and then we introduce something called coefficient of determination, which we use as a R square. Is the square of the coefficient of the correlation, and this will help you later to understand your regression analysis. But for now, I just want to start with this. So the R-square is an important tool in determining the degree of linear correlation of the variables, how goodness of fit is your model in the regression analysis. And of course, I'm going to go back to this R-square. But R-square measures the proportion of the variance, in this case, in the deforestation example, that matches up with the variance in the population density. And basically, the R-square in this case is the square of the R, and this is 0.44. So this, by having a square, if I run this regression, if I run the regression of deforestation and population density, and I obtain my R square, so something like 0.44, I can conclude that the 44% of the cross-country variation in this deforestation can be explained by this cross-country variation to the population density. So this, my X in this case, explain about 44% of the variation in Y in the deforestation. This is an indication how fit, how good is my model, how good is the X's that I include into my model in terms of explaining my dependent variable Y. What I want to highlight in the next slide is that correlation does not imply causality, and this is important for you to understand the distinguish between these two. The correlation between, for example, workers' education level and wages, they can be strongly positive. However, this doesn't mean that the education gonna cause your high earnings. We're not quite sure for this. We need to test this. That's why the correlation is not an enough measurement for us. So there could be two possibilities in this case. Education might improve your skills, and having more skills, you get better job, better paid job. In this case, we can say that education causes your earnings to increase. No, but it could be another option, like individuals are born with a certain quality, let's say A, which is relevant for their success in that education, in that particular job. So, but this quality A does cause earnings to increase. So in this, which we're going to go back again to this causality later in this course, I just want to highlight that correlation does not imply causality. Correlation just measure the strength of the relationship between these two variables, but we're not sure which one caused the other one. An example related to this, why the variables are correlated and which one causes the other one, is suppose that we collect data on some old people on how much they smoke and whether they have cancer and how much they drink. And for example, we use this notation X, how much they smoke, and whether they have cancer with Y. So my Y is the dependent in this case. So what correlation would we find in here? The direct causality might be that positive correlation, the correlation between X and Y in this case, the people who smoke are gonna get cancer. There's a direct causality, smoking causes cancer. However, there might be another variable which we do not be set here. The heavy drinkers tend to smoke, but this does not mean that the smoking gonna cause people to drink. So you can see how this different another variables might have some effect in this case, and you might observe the correlation between Y and Z to be positive in this case as well. The correlation between having a cancer and drinking, but this the third correlation, which is positive here, does not imply that drinking gonna cause the cancer. Basically, that not gonna reflect the causality. This is another example again with our population and density, population density data. Again, high rural population density gonna cause farmers to clear new land and these forest areas, so which in turn is gonna cause deforestation. Here we're going to have again the positive correlation between X and Y, between the population density and deforestation, but there could be another variable which in this case we denote by Z, and this is new land and forest areas that might as well play a role in this relationship. So in this case, X, which is the population density, is an indirect proximate cause of Y, of deforestation, and Z is a direct cause of Y. So the idea here is to highlight here is that sometimes we measure the relationship between X and Y, but there always could be another variable that may have a cause, that might have affect our variables, our main variables of interest. So not to confuse between correlation and causality. And just for to summarize at the end, that correlation can be very suggestive, but cannot on their own establish causality. And in all cases, we need the correlation coefficient between the two variables and a sensible theory that suggests this sort of causality. And of course, more in-depth analysis between the relationship that tests the relationship between these two variables. This is another example here. Again, I plot this correlation XY plot between the house price versus the lot size. For example, these are data that shows me the number of houses sold in a particular area and how they relate to the price of this house, how we relate the sale price of the house, which is now dependent, and X, the lot size of these houses. So we can draw, think of drawing a straight line that's gonna best fit the points in this XY plot, and we can see how by having this XY, the first intuition before we go into any in-depth regression analysis is that we have a positive slope in here, and this would give us a positive correlation between these two variables. What I want to summarize at the end for the today introductory lecture, and for you is just to say that econometrics is an important when we want to measure the relationship between two and more variables. Again, I want to highlight the difference between the types of data sets that we look at, the time series, the cross-sectional panel, and the pool cross-sectional data, and to make distinguish between these two data sets. I'm gonna upload on the website an example Excel file with the example of the different data sets that we can you can look at, and just to make distinguish between these data sets. And when we have the data, we look today at how we can present this data by having the scatter diagrams, either by the line graphs and the histogram. We're going to discuss this, how we do this later in practice by having SCADA software in my head. And we talk about some very first descriptive statistics as the mean, the standard deviation, the quantile percentiles, which were very indicative once we want to look at the distribution. And most importantly, the correlation analysis, which measure the relationship between two variables. And basically that was what I have to say on this very first introductory lectures. Please feel free to send me your questions by emailing me. My email is the very first, I'm sure you're going to have access to this, to the lecture website. This is my email. And in the next course, I'm gonna talk about the more in depth about the regression analysis, the statistical properties of these regressions, and we're gonna get more in depth into the regression analysis. Thank you for participating today, and I hope you enjoy this lecture.